and off we go. Okay, so just like we did last time we met, I made a little bit of an agenda going through each of the sections in the textbook for this topic. I decided to skip over some things that I didn't really see as being particularly relevant to you guys. So what you see in this presentation will hopefully cover everything in the homework. And I'm going to change my mind on what I just said. It will cover everything you see in the homework because I vetted the homework before I made this outline. Okay, so first things first. Topic 4 is all about forces. Okay, so you probably learned a lot of these concepts back in like middle school science. So real quick, I want to talk very briefly about what forces are, different types of forces. Okay, so Mr. Schmitz, if you can unmute the computer, can someone just yell out, what is a force? Common middle school answers. What are they, guys? What is a force? It's a blank or a blank.
Push or a pull.
There you go. Good job. Okay, that's really what a force is. It's a push or a pull on something. Thanks, Mr. Schmitz. So different types of forces that we see in science. So physically pushing something, physically pulling something. Magnetism. Magnets pull on things, guys. Gravity is a force. You've got electrical forces, the forces between atoms. So anything that pushes or pulls on something would constitute a force. Okay. Now, forces are measured in newtons. So the unit of force is the Newton. Okay. Just memorize that. It's the newtons. Now, just like what we talked about in topics 2 and 3 with vectors, force is also a vector, meaning it has blank and blank. Okay. I tried to emphasize as much as I could in topics 2 and 3, but what 2 parts should be a part of every vector?
Magnitude and direction.
There you go. Good job. Somebody's been reading. Magnitude and direction. Okay, good. So I want to take a look at an example. Now, in this topic, we're going to be doing a lot of drawings called free body diagrams. Okay, and basically what that is, it's a very simple picture of all the forces that an object is experiencing at a given time. So for example, suppose that we have this sled that you're pulling through the snow. Okay, and suppose that this string right here, let me pull up my drawing tool. Okay, suppose that this string right here is what you're pulling on the sled with. Okay, so that is what you are pulling on the sled with. So you might be fooled into thinking that that's the only force that the sled is experiencing, but you'd be wrong, because the sled is also experiencing the force of gravity. Gravity is pulling down on it. Okay, and also the snow is pushing up on it. And that might be a little confusing concept to think that the ground is pushing up on the sled at the same time that gravity is pulling down. And we'll talk more about that a little bit later today, hopefully. But just be aware that there are actually 3 forces in this problem. There's the force that you're pulling on the sled with, there's the force of gravity, and there's the force of the snow pushing up on the sled. Okay, so a free body diagram is basically taking all 3 of those force vectors and drawing them on the same coordinate plane. Okay, so what I just circled is a classic free body diagram. You don't have to draw the actual sled when you're drawing a free body diagram. The object you're talking about could be represented just with a dot, as we see in this picture I just circled. Okay, but you can see I've got all 3 of my forces accounted for in this picture. Okay, now we learned last topic that you can break down a force into its components. So this 30-degree force, in the next drawing over, you can see that they've crossed it out and they've broken it into its x component and its y component, and you do that just using SOHCAHTOA. Okay, so you should already be familiar with that. Okay, but the main point, I just want you guys to see what a free body diagram looks like. This middle picture is a classic free body diagram. If you wanted to go deeper and break things up into their x and y components, this diagram on the right is also a great example. Okay, so we haven't really gotten into any math yet. We're just showing you the picture so far. Okay, raise your hand if you have a question at all. Otherwise, we can just keep on going. Okay. I'm not seeing very many people in the room. Are a lot of people gone today?
Yeah, we've lost our. We've had a fair number of students drop.
Okay. Okay. All right. Well, I'm sorry we lost them, but more fun for us, right? Okay. So keeping on going. This is another kind of 8th grade concept you studied probably 4 or 5 years ago. But we have Newton's laws of motion. There's 3 of them. And a lot of them are popular enough that you could probably recite them if I had you fill in some blanks. So, for example, Newton's first law of motion says that an object at rest will stay at rest unless acted upon by some external force. Okay, and similarly, an object in motion will remain in motion unless acted upon by some external force. Okay, so basically Newton's first law of motion, what we just recited. Okay, a word that sums up this concept is inertia. Okay, inertia. So I wanted to go over a couple examples of inertia because it's a term that we don't really use that frequently in pop culture, but it's a very simple concept to understand if you've ever experienced some things. Okay, so I want to talk about a rest example and a motion example. So we just said that an object at rest will stay at rest unless acted upon by some force. So for example, have you guys ever seen those movies where people will whip out a tablecloth from underneath some dishes and the dishes will remain standing? Yeah, I see some nods. Good. That is inertia at rest. So basically, suppose you have like a wine glass or something on a tablecloth. That wine glass has mass to it. Okay, and mass, as a general rule, wants to keep doing what it's doing. So if it's at rest, that wine glass is going to want to stay at rest. So when you try and whip that tablecloth out from under the wine glass, if you do it well enough, that wine glass should not really move at all because of its inertia. It wants to stay at rest. Okay, give me a thumbs up if that makes sense to you. Okay, good. Now let's talk about the motion example. So another classic example, if you've ever been in a car going around a sharp curve, okay, you might notice that as you're going around that sharp curve, your body might slide across the seat. Have you ever experienced that before? Yeah, I mean, everybody has, right? So that's an example where your body is traveling in a certain direction as you're driving towards the curve. As the car makes the curve, your body wants to keep moving in the direction it was originally moving in. Okay, so even bodies that are in motion want to stay that way. So that's why your body slides across that seat when you are on a sharp curve, because of inertia. Okay, so once again, it's a very tricky sounding term, but it's actually a pretty basic idea. Okay, now one more pointing on inertia. Inertia is measured by an object's mass. So don't be fooled by the fact that if something weighs a lot, it's going to have a lot of inertia, because inertia is a concept that revolves around mass, not weight. Okay, and the reason I say that is because weight is dependent on the planet you're on. Okay, mass stays constant anywhere you are in the universe, but weight is dependent on the planet you're on. Okay, so mass is the key factor in determining inertia. All right, so really that's all I want to talk about with Newton's first law of motion. Do we have any questions? Okay, good. Next is where we start to introduce a little bit of math. Okay, I know everybody's probably groaning, thinking, "Oh, math! All we do in this class is math." This is not going to be that bad. Okay, so we get to Newton's second law of motion. Okay, so Newton's second law of motion, you probably can't recite that from 8th grade because there's not really a colloquial phrase that goes along with it like there was for Newton's first law or like Newton's third law does. Newton's second law is really just an equation. We're going to talk about that equation down below, but basically Newton's second law says, right up here, I tried to summarize this in a bullet point. It says there exists a cause and effect relationship between forces and changes in velocity. Okay, so for example, if I'm this guy in the shopping cart, with the shopping cart, if I'm exerting a force on that shopping cart is going to change its velocity. Okay, that's not a very complicated idea. If you push on something, assuming that object moves easily enough, that object will change its velocity. Okay, so that's all Newton's second law is saying. Anytime you exert a force, it's going to change an object's velocity. Okay. Now, there needs to be a discussion about what an external force is and what an internal force. Okay, because we just talked about Newton's first law, which said an object in motion will stay in motion unless acted upon by some external force. Okay, so there are what we call external forces that act on a system, and there are what we call internal forces that act on a system. So suppose for a second that we make our system the guy and the shopping cart. Okay, so I just put a giant box around those two objects in this picture. So as a whole, the guy and the shopping cart make up our system. Okay, so let's talk about external forces. Let's talk about internal forces. Okay, so the force that actually allows the guy to move, first of all, is the force that the floor is pushing back on the guy's foot. Okay, so the guy, as he's running with the shopping cart, now I want you to watch my screen because I want to draw some arrows in here. His foot is exerting a backward force on the floor, represented by this green arrow. Okay, at the same time, the floor is exerting a force forward on the guy's foot at the same time. Now, remember, that's kind of a confusing concept to think about it that way. But we're going to talk more about this when we get to Newton's third law. But just remember that if the guy is moving in the forward direction, something must be pushing him forward. And that thing is the floor. It's kind of a weird thing to think about. Okay, but stay with me. So these guys right here, these are external forces. So those are the forces that are actually causing movement in this system. Okay, now because we're treating the guy in the shopping cart as the system as a whole, you might argue that, well, isn't the guy putting a force on the shopping cart itself? And although that's true, that's what we call an internal force because it's happening within the system. Okay, that force on the shopping cart from the guy's hands isn't really doing much to the system as a whole because we're treating the guy in the shopping cart as a single unit. Okay? Do you understand what I'm saying with that? Give me a thumbs up if you're okay with that concept. Okay, so these are internal forces right here. I'm gonna draw some arrows here. So that's an internal force. We don't really care about it because it's not really a big picture idea. These forces down here, they're causing the motion to happen. Okay, so those are external forces. Those are the ones we care about at the end of the day. Okay, so anyway, that's kind of what I want to talk about, external forces and internal forces. So the next bullet point I wrote down in my agenda is that if you ever want to calculate the net force on an object, or in other words, the total like result of all the pushes and pulls, the net force is a vector sum of all external forces on a system. Now in topic 3, which you guys are catching up on right now, there's a lot of vector sums you guys are doing. That's where we get the breaking down vectors into their components, plugging them into Pythag, and solving that out. So you've been doing this for the past topic or two in this course. Okay, so once again, we're seeing the same kind of math pop up. So basically, if you ever want to find a net force on an object, all you gotta do is add the force vectors. And all you're doing is just using the same techniques we used in topics 2 and 3. Okay, it's just that in topics 2 and 3, you were adding like velocities and accelerations. In this topic, you're adding forces. Same idea though. Okay, so now we get to the meat of Newton's second law. So here's the actual equation. This is probably the most important thing you want to write down for Newton's second law. Okay, so the relationship between force and an object's movement is represented by this equation. It says F net, okay, so F, and then in little subscript letters, the word net, net. So F net is equal to an object's mass multiplied by its acceleration, okay? So F net is equal to mass times acceleration. Now we're going to be practicing that a lot in this topic's homework. It's not a very hard equation to remember though, you're just timing two things together. Okay, so as an example of this, weight is a force. So the earth is pulling down on you right now with a force. So if we were to say, call that force W instead of F net, we could say that weight is equal to your mass times the acceleration due to gravity. And remember, we said to you last topic that the acceleration due to gravity is equal to negative 9.8 meters per second squared. Okay, so that's not really new. We talked about that last time. So basically, you could calculate the gravitational force that the Earth is pulling down on you with right now if you knew your mass in kilograms and if you times it by negative 9.8 meters per second squared. Okay, now that would get you your weight. But what do we measure weight with in the United States? Pounds, yeah. But what did we say the unit of force was in this topic? It was an N word. Newtons, yeah. So even if you did this, if you times your kilogram mass by negative 9.8 meters per second squared, it probably wouldn't mean much to you because it'd be in a unit you're not used to. So just keep that in mind. Also, tell me real quick, even though this kind of seems obvious to me, I want to make sure you guys are on the same page. Why is G's value negative, by the way? What direction is gravity pulling you in? Down. That's why it's negative, okay? Okay, so that's really all there is to this section. Just know that equation. F net is equal to mass times acceleration. Know that you can manipulate it to represent weight situations. And really know what an external force is versus an internal force. Remember, internal forces we don't really care about. They don't really change the problem. It's really the external forces we care about. Okay? Anyway, what I wanted to say right here was just that weight is measured in newtons. Newtons. Okay, not in pounds like we're used to, unfortunately. Okay? All right. Let's go on to the next topic. If you have any burning questions, please just wave your hands like a mad person, or just have Mr. Schmitz unmute you guys, and then you guys can ask me. Okay, so here we get to another kind of 8th grade law of Newton's. Okay, this is another one that's kind of got a colloquial phrase to it. Okay, so you've probably heard that every action has an equal and opposite what? Okay, that's Newton's 3rd law. Good. Now this is where, you know, it can get kind of confusing if you haven't thought about this that much, but it comes back to this idea that if you are a swimmer pushing off on a wall in a pool, you are pushing off on the wall with a force. Okay, at the same time, the wall is pushing off on you. Okay? I don't know, it's always been weird to me just understanding that concept that objects that are stationary push on me at the same time that I push on them. Okay, I've always had trouble with that, but it's a fact, okay? So just get used to that. Now, I want to talk about the free body diagram for this example. So if you take a look here, here's a free body diagram. We have the swimmer represented by a dot. We have the force that the wall is pushing off on her with. We have her weight represented by W. We also have BF. BF stands for the buoyant force. Okay, so this is the weight, this is the force with which water pushes up on her. Okay, so every object that's submerged in a fluid is going to experience a buoyant force. Okay, don't get hung up on that. Just what I really want you guys to see though is that what force is missing from the drawing?
Gravity?
Well, we have gravity. Gravity's our weight, remember? But what force is missing? Do you see how they didn't include the force of her pushing on the wall?
Yeah.
Why do you think they did that? Does it even matter?
Not really.
It doesn't matter. And it's kind of like the internal force idea. I mean, this force, the feet on the wall, is not an internal force because it's not happening within the system. But you can see that the system of interest is just the swimmer. Okay? So we don't really care about that force on the wall because it's outside of the system that we're interested in. So we can just ignore it. Okay? So same idea as the internal force thing. If it doesn't really make a difference at the end of the day, you can kind of just ignore it. Okay? So the free body diagram here on the right, that's really all the forces that are causing motion in this problem. Okay? Give me a thumbs up if you're okay with that. Okay. That's really all there is to Newton's third law, guys. So if you understand the concept that every action has an opposite and equal reaction, if you understand that free body diagrams can sometimes be deceiving because we kind of ignore forces that aren't part of the system, if you understand those two bullet points, you're in pretty good shape for this law. Okay. All right, we're kind of cruising now, and I promise I give you guys plenty of time to work. So I've got basically 2 more things to talk about, and then we're done. Now, Newton's third law said that every action has an opposite and equal reaction. So I wanted to just give you another perspective of this. We have in physics what's called the normal force. Okay. Does someone have a question? Okay, I'm just getting a lot of feedback. I'm not sure if someone's talking right now. Okay, well, we'll keep going. All right, so the normal force. Basically, normal force, whenever you see that term in this course, that's the same thing as the force with which a surface pushes up on an object. So suppose that you're carrying a big bag of dog food. We know that dog food is experiencing gravitational pull, which is why we drew this little weight arrow right here. But at the same time, the bag of dog chow is also experiencing an upward force from your hands. Okay? So that upward force that your hand exerts on the dog chow, we call the normal force. It's the same thing as if you put that dog chow on a table. Weight's pulling it down, but at the same time, the table is pushing up. So that's the normal force. And you can even see, like, the table is sagging right here in this picture, okay? Which is evidence that this table must be doing something to counteract that gravitational pull. Okay, so that's really all normal force is. It's the upward force of a surface that kind of opposes the actions of gravity. Okay, let me type that in real quick, just because I want to make sure you guys get this. And I just got a notification that our meeting is going to kick us off in about 10 minutes. So let's just type this in, and hopefully we can get as much done as we can in the next 10 minutes. So normal force is the force pushing up on an object in opposition to gravity. Okay. It's basically the action-reaction force. Okay. So it's the reaction to gravity, basically. That's the normal force. Okay. Now, I've pasted an example problem in this outline. Because we're probably not going to get around to it with the time we have left, I will make a video of this example problem and post it to the announcements within the next day or two. I mean, you guys are catching up anyway. So are you okay if I post this maybe tonight or tomorrow instead of going over it right now?
Yeah.
Okay, I feel like that'll help you guys catch up a little bit better on topics 2 and 3. Okay, so stay tuned for that. Another type of force that we're going to talk about is tension force. Okay, so tension basically exists in an object that is attached to a string or a rope of some sort. Okay, so here's the technical definition. It's the force along the length of a medium, especially force carried by a flexible medium such as a rope or a cable. It's very wordy. All I want you to know really is that tension is just the force of a rope or a string on an object. So here we have a caveman or some guy with a loincloth. I don't know why he has a loincloth. Weird. But you can see he was holding onto a rope. Okay, so if you were to analyze the forces taking part in this problem, you have the guy's weight, which is pulling down on his mass. You have the tension force, which is the force that's pulling up on the guy. Okay, and according to Newton's law, that tension force should have an action-reaction force to it. Okay, so basically, the tension is basically the force that's pulling the guy up. So that's the tension right there. We represent it with a T. That's tension force. Okay. So for example, they're asking you this question: what's the tension in the rope if the man has a mass of 70 kilograms? Okay. Well, Newton's second law said that force is equal to mass times acceleration, right? Okay. So if we know that gravity is my acceleration that this guy is experiencing, so at negative 9.8, I'm going to plug in for A. If I know that the man has a mass of 70 kilos, I'm going to plug in 70 for kilos, and all I got to do is times those two numbers together, and that's going to give me the tension force. Okay? Turns out that that's exactly the same thing as his weight. Okay? Because we're timesing his mass by a gravitational pull. So in this case, the tension is the exact same thing as the weight. It's just that gravity is pulling down while the tension is pulling up. Okay. All right, we're down to the wire here. I got to get off or else we're going to get kicked off. Here's another more complicated example problem with tension. I will post a video on this as well. So next time you guys are in class on Wednesday, I think it is, make sure you just eyeball these videos for me real quick that I'm going to be posting so you can understand the math that's involved. Okay, that's really all I had for you today. So are there any questions?
No.
Okay, now I'm going to give you guys a little bit of time to get all these assignments done for topic 4. So is it fair to you if we make these assignments due October 13th? That's 2 weeks from last night.
Yeah. Yes.
Okay. Yeah, I'm going to give you guys a little bit longer because I know you're catching up, but keep that in the back of your minds. Write that down if you haven't already. Next Friday, or next Sunday, excuse me, not this coming Sunday, but the Sunday after that, I'd like these assignments to be turned in. Okay, keep doing topics 2 and 3 though, as quickly as you can so we can get those grades updated. If you have questions, email me. Otherwise, you guys have a great day. Good luck, and we'll hear from you next time, okay?
Thank you. Thank you.
All right, we'll see you later.